Powerful Python people, I am Professor John Gallagher, and in this CircuitPython school video, we are going to become masterful manipulators of mice. In the prior lesson, we learned to use the HID library to send keyboard input via a microcontroller, but in this lesson, we'll learn how to mimic mouse movements, wheel scrolls, and mouse button presses using that same library. And when we're done, we will have written code that allows us to prototype a glove-based mouse alternative with finger taps mimicking mouse clicks. Now, living in a 125-year-old New England house, we unfortunately have our fair share of mice, but they're all hidden in the walls. Now, while not a mouse, joining me for today's lesson is Artie the guinea pig. He asks that we keep him away from any real pythons, but otherwise he says, let's code. As we learned previously, HID stands for Human Interface Device, and the HID libraries allow us to use CircuitPython to mimic keyboards, which you've done with great success in the prior video, and mice, which we'll mimic now. Now, to work with mouse HID, we need to import USB_HID, just as we did before, and also import from Adafruit_HID.mouse import mouse. Then we create a mouse object from the mouse class that we just imported, passing in USB_HID.devices, which is predefined inside of the USB-HID library that we imported above. And so you'll use these three lines anytime you want to set up CircuitPython for mouse work. Now here is how you can control mouse movements. And note, this is a bit different from your standard geometry. The origin 0, 0 isn't in the lower left, it's in the upper left. The X coordinate is the horizontal on your screen, left and right. Positive moves right, negative moves left. And the Y coordinate is the vertical coordinate on your screen. Negative moves up and positive moves down. So this is how we nudge the current mouse location in different directions. For example, we can call the move method on our mouse object and pass in x equals 100, and this is going to move the mouse right 100 units. And you'll see that jump instantly. Pass in x equals negative 200, and that will move the mouse left 200 units. Pass in y equals 300, that'll move the mouse down 300 units, while passing in y equals negative 400 will jump the mouse up 400 units. And we can actually try this in the REPL in Moo. Let's see. So my board's plugged in, I've opened the terminal in PyCharm, I'm going to get into TO, and I'll Control-C to break any program that might be running, and I'll press return to get into the REPL's 3 chevron prompt. And now let's import the files and set up the mouse, and to do that we'll use the 3 lines shown on the previous slide. That's import USB_HID, then return, and on the next line, from Adafruit_HID.mouse, import capital M mouse. And then to create the mouse object, we're going to call that mouse equals capital M mouse, and in parentheses, USB_HID.devices. And now our mouse object is set up, and we can call the move method on that mouse object. So without pressing return, I'm going to type the following: mouse.move, and in parentheses, x equals 400, close parentheses. Don't press return yet. I'm going to move my mouse to the center of the screen, and when I press return, I should see the mouse jump 400 units to the right. And there it goes, an instant jump. Nice work. Now let's head back. So I'm going to press up arrow. Remember, that's the trick in the REPL that re-enters the prior command that we entered into the REPL. And I'm going to change the value 400 to negative 400 without pressing return. And then I'll position my mouse in the center again, then press return. We immediately jump the mouse to the left using CircuitPython code. Cool skill. And note, we can do the same with y coordinates, and we can send both x and y changes to the move method just by separating them with a comma. So let's try this. And again, don't press return once we type this line. Mouse.move, and in parentheses we'll say x equals negative 300, comma, y equals negative 300. Now I'll position my mouse in the center without pressing return, and where do you think the mouse will move when I press return? Think about that. And here we go. Press return. Did you guess up and to the left? Because if you did, you are correct. Now another few things to note. You can't move your cursor any further than the edges of the screen. So let's try this. We'll type in mouse.move, and in parentheses, x equals negative 30,000. But don't press return. And I used negative 30,000 simply because it's an absurdly large value. I'm pretty sure no one watching this video has a screen that big, but if you do, wow. Then I'll move the mouse to the center of the screen, and now press return. And my mouse stops at x equals 0, which is the first unit at the far left. Now let me show you some more examples of going the other way. If your mouse is a pointer or other cursor that has the click point in the upper left-hand corner of the cursor image, then that click point on the cursor will stop wherever you move the mouse. But if you go all the way to the right, like I'm doing here in the menu bar, the rest of the mouse is being drawn off screen, so it looks like the mouse has disappeared. It's not, it's just on one little point in the far right, but you can't see your mouse anymore. So let's try this in code. If I enter mouse.move and in parentheses x equals, how about 10,000 this time, and then I move my mouse to the top where it looks like a pointer, then press return, it looks like the mouse disappeared, but it's still there, it's just hanging off screen, and if you move your mouse the tiniest bit to the left, you'll see it emerge. Now I'll move my mouse to the center of the code editor. Mouse is the I-beam cursor. Then if I up arrow and press return, I see the left half of this cursor that is arrow pointing in the left and right directions where you can click on and resize the window. Now on to the next slide where we'll learn more commands that we can use. Now we can mimic the scrolling of a mouse wheel, or if you're using a trackpad like the one on the MacBook, that would be a 2-finger push. And now in this example down here, mouse.move passing in wheel equals 150 will mimic a mouse wheel push away from the user 150 units, and mouse.move passing in wheel equals minus 250 will mimic a mouse wheel or 2-finger pull toward the user 250 units. So let's try this back in the Move REPL. We can use the mouse wheel or 2-finger push to scroll the console area. And if I want to scroll up, and remember there's a chance that your computer is configured to move in the other direction, but on the way that I have my Mac set up, if I pull the mouse wheel down or do a 2-finger pull down, then I scroll up in my text. If I push up, the text scrolls down. So I'm going to use a negative value, but if you're configured to move in the other direction, then use a positive value. So I'll enter this, mouse.move, and in parentheses, wheel equals negative 300. And when we press return, we can see that the console text moved up. Nice! Now back in the slides, there are a few more commands I want to tell you about. The commands for mouse clicks are tougher to mimic in the REPL because once you use the press method, your computer will act as if a mouse button is being pressed and remains held down. And to let go of the button, you have to enter another command to release the button or release all of the buttons, but that can be tough to do because if you've just used the REPL to press down the mouse button, then you might not be able to type in the REPL because your mouse button is being held down. But these commands work great in your CircuitPython code, so use them if you need to, and you may need to use at least one of these in the challenge, mouse.press, and then in parentheses, either mouse.left button or mouse.right button. But know that if you use any of these commands, any subsequent move commands you issue, like moving the XY coordinate or moving the wheel, will seem like you're clicking and dragging or clicking and scrolling. So when you're ready to stop holding down the mouse, you want to issue the command mouse.release, then pass in either mouse.left button or mouse.right button, or you can use mouse.release_all, and that releases all current mouse presses. And if you ever do get stuck, you can just unplug your microcontroller, and that'll stop any HID commands issued in CircuitPython that might be holding your mouse button down. So now that we know how to use these commands, it's time for a challenge. In this challenge, I want you to write code and prototype a glove mouse. So I have my CPB mounted to the back of my hand. I'm using an old wrist support glove without the metal inside of it, but you can use a sock or any glove that you have around. And I've mounted my CPB to the back of my hand, and when I tilt my hand to the right, I move the mouse to the right. For a bonus, if you tilt a little more, you can make the mouse move even faster. Then if you tilt to the left, the mouse moves to the left. Again, for a bonus, more extreme tilt would lead to faster movement to the left. If you tilt your hand forward, fingers down, the mouse should move up screen. And if you tilt it back with your fingers pointing up and your wrist moving down, the mouse should move down screen. Now I'm also using capacitive touch with A1 as the left mouse button and A2 as the right mouse button. Now if you don't have fingerless gloves, to prototype this you could use a sock or a regular glove or even tape it to the back of your hand and just use your other hand to touch the A1 or A2 pads on your CPB. But I put the ends of the alligator clips on the palms of my hands so that I can reach them easily just by bending my fingers down, and as long as I'm pressing the A1 or the A2 clip, it's as if I'm holding down that particular mouse button. So as you see here, I can make a text selection, I can scroll. If I let go, it's like letting go of the button. So this is pretty neat, and you've got the skills to be able to build this. So you can pause and read through this if you want a more detailed description of the challenge. If you need to open up prior code dealing with capacitive touch and the accelerometer and then assemble your challenge using pieces harvested from your prior work, why don't you go ahead and do that? And these diagrams here also might help you think about how to use the accelerometer for mouse movements. If you tilt the CPB to the right, that sets the accelerometer's X value negative. But when you do that, you want to send a positive X value using that mouse.move method that we just learned about. And if you have a positive X accelerometer value, you want to send a negative value to the X coordinate. Now the Y coordinates are in the same direction, so a negative Y accelerometer reading would mean that you are pushing the top part of your sensor down, which would mean that you want to move the mouse up on screen, and to do that you would send also a negative y value. And if you push your wrist down and your fingers up in the air, that tilts the accelerometer so that you get a positive value. So you should pass a positive y value into the mouse's .move method. I suggest at first moving up, down, left, or right 2 units at a time. But if you want to go for that bonus stretch goal, then you can try to use the accelerometer to detect an even more extreme tilt. And if that happens, then you can try to move the mouse faster, say 10 units at a time. So why don't you give this a shot? Pause. Work through this. It is a good skills challenge at this point in your CircuitPython career, but I know you are up for it. And when you're ready, resume, and let's compare answers. So up top, why don't we enter the comment HID_mouse_glove.py, and then I'm going to import all the libraries I need. So import board, time, analog IO, digital IO, touch IO, bus IO, Adafruit_LIS3DH. That's our accelerometer. And also remember what we need to import in order to use HID and our HID mouse. That's import USB_HID, and then from Adafruit_HID.mouse, import M mouse. Then we'll define a mouse object that we call mouse. So we'll say mouse equals M mouse, and in parentheses USB_HID.devices. Then we'll define our accelerometer, and this is the same way we did it in earlier videos. If you need a refresher, you can go back and check out those videos. But these lines are first to define our I2C object. I2C is what we'll call it, and we'll set that equal to busIO.I to C. Now in the accelerometer intro, we mentioned that this device is connected via a communication mechanism called I2C, written as I2C. And what we're doing here is setting up an I2C object to use this. Now sometimes in CircuitPython, we'll just create an I2C device passing nothing in, using a command like this, board.I to C, and open and close parentheses. You'll see this in future videos when we work with other boards, but here, working with the Circuit Playground, the accelerometer is built in. So we're not using the standard I2C, but for the Circuit Playground Bluefruit or Express, we need to pass in the specific locations of that built-in SCL and SDA, and we're going to use busIO instead of board. So after busIO.I2C in parentheses, we pass in board.accelerometer_SCL, and that's in all caps, board. And in all caps, accelerometer_SDA. Then we'll set up the interrupt. We'll call that INT1 equals digital IO dot D digital I in O out. And then in parentheses, we pass in board.accelerometer_interrupt in all caps. And then we'll create an accelerometer object called accelerometer, and we'll set that equal to Adafruit_LIS3DH dot, in all caps, LIS3DH _I2C. And then in parens, we'll pass in I2C, that's in lowercase, address equals 0x19. Use a lowercase x. INT1 equals INT1, and that is a 1, not a lowercase l. Make sure you get a 1 in there. And then we'll set our accelerometer range. Accelerometer.range equals, and I'm going to set mine up to the 8G range. So I'll say Adafruit_LIS3DH dot range _8_G. And the range and the G are in all caps as well. Then let's set up our touchpads, A1 and A2. Since we just need 2 touchpads, we're not going to use our for loop technique that we used in prior videos. We'll use the first technique that we learned. That's just touchpad underscore, and we'll call that A1 equals touchIO.T touch I in, and in parentheses, we'll pass in board.A1, and then we'll do the same below, touchpad underscore A2 equals touchIO.touch in board A2. And I'll add a print statement that says HID glove running. Then we'll start our while true loop, while true, colon. So let's get the accelerometer values and print those. Normally we see x, y, z, but since we're not going to use z, I can put an underscore in here so I don't create the unused variable, and we'll have that equal accelerometer.acceleration. And you don't have to, but just to verify we have our values, we'll say print and in parentheses x, y. So everything up into this point is pretty standard, but here is where we handle scrolling, and I want to show you a couple of options. This second one is more efficient and smoother, and it gives us a chance to introduce the math library for accessing math functions. So on the left, this is how I originally handled scrolling. I found a range where I wanted to scroll slowly between positive or negative 1.5 and 3 on the accelerometer's x value, depending on the scroll direction, and 1.5 and 2.5 on the y value. Then I moved the value by 2 if I was in that range, and if the value was more extreme than positive or negative 3 for x, or more extreme than positive or negative 2.5 for y, I moved by 10. And this works. So if your code looks like this, you've met the challenge. But I knew I could do better for two reasons. One, this code results in stair-like movement because I'd move X and then Y. But also, since there were only two mouse movement values, 2 and 10, or -2 and -10, the glove movement was less fluid. It jumped from 2 to 10 points without any scaling in between values. So to fix this, I experimented with raising the accelerometer coordinates to a power using the pow function. For example, pow 2, 3 is 2 raised to the third power, which is 8. Now, pow is available in Python, and it's built in, so you don't need to add a CircuitPython library to the lib folder, but you do have to import the math module. And math has all sorts of useful functions: absolute value, which we'll use in just a bit, sine, cosine. You can search online to see what's available. Now, by raising the accelerometer x or y coordinates to a power, we can scale how much we want to move the mouse coordinates, increasing more severely if we tilt more severely. Now, this is almost an okay solution, but there's still a problem. Sometimes our accelerometer values are negative, and if we raise a negative value to a whole number, there's no problem. We can do that, but if you try to raise a negative value to a decimal because maybe the whole number values that you try to raise to the power are more extreme than you want, then we're trying to raise a partial root of a negative, which is an imaginary number, and we can't do that. Now, if you forgot some of your middle school or your high school math on negative square roots, you can be forgiven. We don't usually use imaginary numbers or try to take negative square roots in everyday math, but to demonstrate this, if I break out Google Sheets and I try with something like this, equals pow -1.5, 2.5, you get an error like this. Power evaluates to an imaginary number. Again, we can't raise a negative value to a power with a decimal in it because that's going to give us a number we can't use. But this code takes care of that problem. We first make sure that any value that we raise is positive. So we use the absolute value to get rid of any negative that might be in front of that. We get the absolute value with the ABS function, and we also get that when we import math. And then we make sure that we set the sign properly. A negative x accelerometer value should give us a positive mouse value and vice versa, while the negative y accelerometer value should also give us a negative y mouse value. Then we move the x and the y together. It's much smoother, and as an extra bonus, we learned about the math library, and we have less code. Now, before we continue, remember we're going to be working with math functions, so I'm going to go up to the top and I'm going to import math, adding the math library to the end of my import statements here. Then we're going to raise the absolute value of the x accelerometer value to the power of 2.5 and convert it to an integer. So I'm going to save the x coordinate moves I want to make in my mouse to a variable called x_move, and I'll set that equal to int open parens pow open parens abs open parens x close paren comma 2.5. That'll take the absolute value of x to the 2.5 power, and then close paren. Then in the next line, I'm going to say if x is greater than 0, colon. And what I'm going to do is I'm going to check to see if the original x accelerometer value is positive, and if it is, I need to make the mouse x value negative. Remember, we showed this diagram pointing out that a negative x accelerometer value should be a positive x mouse movement and vice versa. So if the x accelerometer value is greater than 0, we'll just flip the sign in the x mouse move. So we'll set x_move equals negative x_move. And then our y move is going to be pretty similar. I'll create a variable called y_move equals int open parens pow open parens abs open parens y close paren comma 3 close paren. And again, we really didn't have to worry about the absolute value here because we're raising to the power of 3, which is a whole number rather than a decimal value. But it's good to keep this in here in case you want to change that 3 value to alter the y scale. Then we'll say if y is less than 0, colon. And what we want to do here is if we get a negative y accelerometer value, we want to make sure that we have a negative y mouse value. So in the next line, we say y_move equals negative y_move. Then we outdent and we actually perform our mouse move with the statement mouse.move and in parentheses x_move, comma y_move. Cool, our mouse movements are done. Now let's add touchpad support for left button and right button. A1 will be the left button, so we do that with if touchpad_A1 dot value colon, and then just mouse dot press and pass in parentheses M mouse dot all caps left underscore button. Else, this is where we release the mouse colon mouse dot release, and then in parentheses same thing M mouse dot all caps left underscore button. Then below that, same thing, but for touchpad A2 and the right mouse button. So we'll say if touchpad_A2 dot value colon mouse dot press passing in M mouse dot all caps right underscore button, else colon mouse dot release and in parentheses M mouse dot right underscore button. Excellent. So in the terminal with TO running, save, We see the values printing out, looking good. Now you don't even need the glove. You can tape the CPB to the back of a sock or even just hold it in your two hands and move it left and right. But I wanted to really mimic the glove effect, so I used an old wrist splint but removed the metal bars so that I can move my wrist. And I used a bit of Velcro tape to attach the back of the CPB to the glove. I have A1 and A2 connected to alligator clips. Then I've looped those around to the palm side of my glove so that I can touch them by bending my fingers to control the left and right mouse presses. Then I put my glove on, and lab cat Admiral Grace shows a little bit of curiosity. Then she leaves when I plug in the CPB, and now since I've unplugged my CPB, I need to restart my code in Moo. Now this isn't a mobile project because I'm sending commands over the USB port, so the CPB needs to be plugged into the USB port of the computer that I'm going to control with the code running. And now to show this in action, I pulled up an old Google Doc. I also teach a course where the students build iPhone apps, and in that course they build an app celebrating women in computing, so this is just the text they can copy and paste and use when they build that app. But you can see as I tilt the CPB up, my cursor moves down. If I tilt it down, the cursor moves in the other direction. Right moves right, left moves left. Now I'm going to move my cursor to the beginning of the names. I'll touch and hold down A1 while I move my wrist up, and notice that highlights these names. Then I'll release my finger from A1, then I'll press A2. Notice that the pop-up menu shows up. I can move my cursor to cut and then press A1 on top of cut, and I've cut the names. Then I'll move my cursor, try to get it just below where it says text for women in computing question. Touch A1 to position my cursor there, touch A2 to bring up the context menu, move my cursor over to paste, touch A1 on top of paste, and I've pasted in the text that I just cut. Nice work! So I hope you've enjoyed learning how to work with the HID libraries for mouse control. And don't forget to save this to your CircuitPython school folder as HID_mouse_glove.py and close that external tab. And if you did enjoy this, please drop a like and a comment. It gets lonely making YouTube videos if you don't hear from the people who watch. Also feel free to kindly tell others about the channel. I hope you're feeling good about your skills. Keep coding and watching because there's lots more to come.